Alright, so far for our truss analysis, we have gone over what the supports look like, where we get our resultant forces from, or our reaction forces. And we've gone over loads as well, where we've done loads have to be on a point, and they have a direction and a magnitude. And so what we're going to do today is we're going to go over and discuss what equilibrium means, and I'm going to show an example of how to solve it. Again, rolling supports, the supports that have the wheels on them, they can only provide forces in a direction that's perpendicular to the wheels, and a pin support can provide forces in all directions. So let's go over to equilibrium. Equilibrium meaning equal, and the reason why we use equilibrium is we have our big engineering formula over here, F equals ma. It's used, it is describing if you have any object that has a mass, which is most objects in our real world have a mass. If we put a force on them, they will accelerate. With our bridges, and if we consider bridges, buildings, civil structures in general, we do not want our civil structure to move, because as soon as our civil structure has any form of acceleration, it's usually falling down. So we want to have our civil structure to have a zero acceleration, so it's not moving. But because we live in the real world where our mass exists, so mass is a real number, so whatever it is, a real number times zero, our force is going to equal zero. Now, F equals ma can be broken down into our total force. So we're already breaking down our F into these two equations over here, where we are saying the sum of all forces in the vertical direction, so this arrow over here going up, the sum of all the forces in the vertical direction has to equal zero. The sum of all the horizontal forces has to equal zero. So what we're saying here is, if we get all our verticals equal to zero and all our horizontals equal to zero, there is no net force. Therefore, there is going to be no net acceleration, which is what we want for our bridges. We also have moments. This over here, this is a lowercase m, I believe, for mass, and this is a uppercase m, but this is our moments. And the best way to think of it, force, because force is a vector, has a direction and a magnitude. Forces is like linear, that's going to go straight. Moments is the equivalent of force, but in a rotation. So if you want something to spin, you're going to be introducing a moment. Just like if you want to move an object, you're going to put a force. If you want an object to rotate, you're going to put a moment. So the same logic, we don't want our bridge to spin around. We're going to say the sum of all moments on the bridge, or sorry, on the civil structure has to equal zero. And I think, I'm actually not sure if that's a capital or lowercase. I think it's uppercase. I think this is uppercase, and I think mass is lowercase m. Alright, so what's our next page? Well, we have loads, we don't need loads. So let's go and do a solving. I already have that question over there on the side of the page, which I've already solved by putting into a simulator. But let me explain where we got that question from. I'm just doing a simple case where we have a truss. This is probably one of the simplest trusses we can get, where we have 1, 2, 3 members. We have, for our nodes, we have 3 nodes, because a member is a single element. A node is where we're connecting 2 or more members together. So these 2 members are joining here, these 2 members are joining here, these 2 members are joining here. So we have 1, 2, 3 nodes. We have, just writing the scenario down here, we're going to have a pin joint, and I'm going to denote that by having this icon over here. And over here, I'm going to have a rolling support. Then, where'd my red pen go? Okay. Then I'm going to introduce a load. So, like we were saying with our load, you have to introduce a load on a node. You can't put it in the middle of a member. So in this example, I'm going to say where this triangle over here is, I'm going to introduce a load over there, and I believe I have 50 newtons. 50 newtons. All right, so we have the load going down there. The first thing we're going to do when we have this scenario, in order for us to solve it, we have to first, there are still some extra forces in this scenario, because we have a bridge over here. We have a force going down, a 50 Newton force. If we go back to what our equilibrium formulas are, I'm just going to write that over here. Sum of all forces vertical equals 0. Sum of all forces horizontal equals 0. and sum of all moments equals 0. So if we really look at sum of all forces vertical, in this scenario, the sum of all forces vertical does not equal 0. Because right now we have a 50 newtons going down, and so that does not equal 0. So we know that there's some missing force in this equation. So we're going to go to our information where we were talking about our supports. If we go back to our page where we're talking about our supports, we know that our supports have their own reaction forces in there, where rolling supports have either a force vertical or horizontal. Has a force that's perpendicular to the motion. Notice this one over here, it's perpendicular. We don't know whether it's up or down, but we know that the direction has to be vertical for this top one, and this one's horizontal. A pin can be any direction. So, but we're gonna split it up into vertical and horizontal components, just so it's going to make these equations easier to solve. So let's look at the first one where we have the rolling support over here. Do I have a ruler? Oh, I do. Nice. We have this rolling support over here. We know that this is going to have a force that's going to be either vertical or horizontal. So it's going to be vertical. We just don't know whether it's going to be vertical up or vertical down, but we know it's going to be a vertical force, so we're just going to draw it as like an arrow going vertical. This over here is a pin support, so we know this one is going to have a force going vertical, but it also could have a horizontal force. Right, now the first thing we do is when I draw these, when I'm drawing out these questions, notice how I already changed the colors of these, so I'm already making a mental note that anything that I draw the color of red in means this might not be correct, right? Even though this is vertical up, as a result from the equation, it might be down, but we know that the direction has to be there. We also might see that this over here, this arrow is going to the right, but when we do our sum of all forces horizontal, there's no other horizontal forces, so this one is going to equal 0. But I digress, we will get to that later. Alright, so now we have drawn all the forces and all the all the reaction forces in this scenario. We are now able to solve it. So let's start by doing some equations. We can say sum of all forces, let's start with sum of all forces horizontal, because that's the easiest one to show by this example over here. If we say sum of all forces horizontal equals 0. The first thing we have to do is we have to define what is a positive force. So what I'm going to do on the side here, I'm just going to make a note to myself and say, we're going to say that up is positive, we're going to say that right is positive, and we'll say that clockwise is positive. That's just so when we get our notation when we're explaining our things. So forces horizontal equals 0. 0 is going to equal this force over here. Oh, I should name these. Let's name this as A, and let's name this as C. So this over here is going to be our force vertical C. Yep, and this over here can be our force vertical A, and this could be our force horizontal A, just so when we can start to write these in the equations here. So we say 0. 0 equals force horizontal A. We're going to say it's a positive because it's going to the right, and there's nothing else in this equation. There's nothing else here that has a horizontal force. So what this is telling us is that the force HA has to equal 0. So we've already eliminated this in our equation. Easy. So now let's talk about something a bit more difficult, where we have our sum of all forces vertical equals 0. So let's get all our vertical forces. And just for the simplicity of this video and explaining to you, let's go from left to right. Let's start over here. Our first is this one, which is our force VA. And in our example over here, we said up. So we're going to assume that we're correct, and we'll say positive. So plus force VA. Then we have our next force is this one over here, our 50 newtons. So we'll say minus 50 newtons. And it's negative because it's going down. And then we have this one over here. We have positive force VC. The issue we have here when we try to solve this is let's look at the amount of unknowns we have. We have this is an unknown and we have this is an unknown. So we have two unknowns in a single equation. It's a relationship, but we cannot solve this. So we need to introduce, if you have an equation that, if you find some other relationship between these two forces, like if you have something with force horizontal, you can use simultaneous equations to solve it. But let's go even simpler than that. We can use our third equation over here. So we're going to use our sum of all moments equals 0. So before we do this, we'll do a quick revision on what is a moment, because you would have definitely learnt it in year 11, but let's just go over it again for the sake of solving this particular style of question. So what is a moment? Moment equals force times distance. All right. We know what our force is. Force is in newtons, and our distance has to be perpendicular distance. Perpendicular distance. I probably spelled perpendicular incorrect, but that icon should explain it. So we need our perpendicular distance. So if we have a thing over here, a pivot point, so everything's going to rotate around here, and we have a length over here. If I have a force going here, and this force is 10 newtons, and I have this length over here is 5 meters, right, we can find that our moment here is going to be moment equals 10 times 5 is going to equal 50, and the unit of measurement for this is Newton meters. I think it's capital. 50 Newton meters. Yeah, we've got to just find that perpendicular distance and times that. What this means is if we get to any scenario where we're going to have our moment equals F times D, if we ever get to a point where our D is equal to 0, it doesn't matter how big our force is, our moment is going to equal 0. So we use this particular exploit over here to solve this question over here. When we want to do our moments, right, we have 3 unknowns in this scenario. Well, we've already found one. We have 2 unknowns in this scenario. So when we want to calculate our moment, if we calculate our moment where our distance is equal to 0 for one of these forces, we can solve this moment. So let's say we're going to do the moments about point A. So what I'm going to do over here is we say sum of all moments equals 0. We can say, all right, we want to do sum of all moments. Let's find it around point A, just so we can explain what's happening here. And clockwise is going to be our positive. We have our first point over here where we have force VA times 0, because its distance is 0. So we could eliminate that one, but I'm just going to write it to show you that we eliminated it. And that would be, well, 0. It doesn't matter if it was positive or negative. Then let's do this 50 over here. Oh, I need to show you some distances. This over here is 2 meters, and this over here is 1 meter high. So this over here, this 50 newtons is minus 50 because its distance, its force is 50, and its distance is 1 meter because it's in the middle of this 2. We have that, and then our last force is this one over here, where we're going to have force VC. We don't know what force VC is, but we know its distance is 2. And this over here is going to be, if we have the bridge over here and this is going up, it's going to be counterclockwise. If you think of it like a steering wheel, it's rotating counterclockwise. So it's going to be, oh, my mistake. This one's going to be negative. This 50 is actually going to be clockwise. 50 times 1 is clockwise. Make sure you fix that up if you followed that mistake with me. We then solve this equation. Let me just clean it up a bit. 50 minus force VC times 2, which means force VC equals 50 over 2, which equals 25 newtons. So we now know that this force over here is 25 newtons. We can write that down over here. 25 newtons. We could also write this is equal to 0 newtons because we figured that one. So now we've found this is 25. If we plug this 25 into this equation, we can then find out what FVA equals, because this is now the only unknown. And if we solve that, we're going to get FVA equals 50 newtons minus 25 newtons. So it's going to equal 25 newtons as well. And so what we've done here is we have identified we have found our two reaction forces. We can expand this if we have a scenario where we have more forces all over the place. We just have to add more of them into the equation. The limiting factor in this is that as long as we have three equations, we can solve for three unknowns. Which is why when we're solving these equations, we need to solve a pin joint and a rolling support. Because these have three unknowns. If we had two pin supports, that is four unknowns, and that's too many unknowns for the amount of equations we have. I'm just gonna... Alright, so we have our 25 reaction forces. So now what we're going to do is, to solve this whole truss, we're going to, by solving, I mean, we want to find the individual force on each of the members. This can be relevant if we're making a bridge and we know that we have a piece of metal that will fail if it is experiencing a force that's like over 100 newtons. We can do this by, we can do our truss and we can identify which of the members is close to 100 newtons or whatnot like that. So we can find out the force that the structure is experiencing. So the reason why we're using truss analysis is that it allows us to do this next step. We can find what forces it's experiencing because we can zoom into an individual part of the bridge. So let's, do I have my highlighters here? I do, yes. Alright, so what we're going to do is we're going to zoom into this part of the bridge over here that I've measured in pastel green. And I'm going to go to my next page and I'm going to draw this part. So what we have over here, we have this over here is like a triangle. If we consider this as 1 by 1, so this is going to be 45 degrees, and we have this as a 25 force going up. So I'm just going to draw that on the next page. So if we go to this page over here, if we have this particular shape looks like this, right? Well, I just want to draw this particular node where we have 25 newtons going up. We don't know, we know this is at 45 degrees because based on the geometry of the question. We have, these are members that we've like cut in half because we're just zooming in on like this particular element of the bridge. But why we do our truss analysis is by one of our definitions we made for our nodes is we said that the particular force has to go, it has to be either, it has to be in the direction of the member. So this one over here has to either be going to the left or to the right. This one over here has to be diagonal, either towards or away from the node. That's by the definition of the simplified case we did for our members. They can only handle the force in that direction. So now we have to do our first step of deductive reasoning, or sometimes guessing, but in this particular one we can do our deductive reasoning. We know, again, our formulas for equilibrium, because if the bridge is under equilibrium, or the structure is under equilibrium, each individual component of the bridge has to also be under equilibrium, because part of the bridge isn't falling compared to another part. The whole bridge is stationary. So if we do our sum of all forces vertical equals 0, sum of all forces horizontal equals 0, and we can do sum of all moments equals 0, even though we're not going to use this last one for this particular equation. Just like we did with this question, where we said if we identified if we have a force going down here, in order for it to equal 0, there has to be some force going up. Because if we have negative, something has to be positive for us to get to 0. By that same reasoning over here, this over here is a 25 Newton force going up, so we need something to go down in order for our sum of all forces vertical to equal 0. This is where we say, well, okay, we have these pairs of forces, either this one or this one. Which one of these two forces can in any way impact a horizontal force? Sorry, a vertical force. This part over here cannot affect a vertical force because it is purely horizontal. No matter how much force we put in here, it's only a horizontal component, so it's not going to interact. This one over here can interact because it's diagonal, so it's going to have part vertical and part horizontal components. And so then if we know here, if this is going up, we need, out of these two lines, which one has a portion of it going down. It's clearly this one over here. is the one that's going down. So I'll just delete the other one. So we have this force going up. This force over here has to be going down. Then we'll look at the next equation where we look at sum of all forces horizontal equals 0. We have this. We've already determined this one is going to the left. So for the same reasoning, this can't have any horizontal components. It has to all be counted by this. And if this is going to the left, this one has to be going to the right. So that's how we eliminate this force over here. And so now we have defined, well, we know this is going up, this is going to the down right, sorry, down left, and this is going to the right. So we can now, and let's also start labeling these things over here. So if we say this is A, C, let's call this B. So we can label this over here as this can be our force A, B, and this could be our force A, C, because that's what we can call these members. So we can start doing some equations now to solve this. We can go back to our sum of all forces vertical equals 0. We can start writing that out. And we know we have, okay, positive 25 newtons. Then we start to deal what is probably the more difficult maths part, which is not saying a lot, but is our trigonometry. We have over here, we have our force AB is going down at a 45-degree angle. So if we were to draw that as a 45-degree angle, it's like this. The force is going down like that, and we can break that down into vertical and horizontal components. And if we say this is our force AB, and this is at 45 degrees, and we say this could be our vertical component, and this could be our horizontal component, we can use basic trigonometry to find out what these individual values are. And I believe that would be, this would be, pause. So sine 45 is going to equal, sine is opposite, right? So that's V over FAB. So then V is going to equal sine 45 times FAB. And because we're dealing with trigonometry, we can know this one is going to be, H is going to equal cos 45 times FAB. And we're lucky because 45, they're obviously equal. But obviously as the angle changes, that could be different. So what we've done here is we've broken this down into horizontal and vertical components. So our vertical, sum of all forces vertical equals 0. We have plus 25. We have our vertical component of this over here, sine 45 times FAB. And it's down, so it's going to be negative. So minus sine 45 times FAB. Then FAB is going to equal 25 divided by sine 45. And if we plug that into one of our calculators, we should have 25 over sine 45 equals 35.35. And luckily I have the simulation there just to double check that my answers are good. 35.35, and this is in newtons. So what we've done here is we've already solved for one member what the force is. We've already solved it. This is 35.5. In order to keep this sum of all forces vertical equals 0, we need this member to be experiencing 35.35 newtons of force. All right, and we can do the same thing with our horizontal now. We can go sum of all forces horizontal equals 0. We know that we have our positive FAC, and our negative is going to be this one. So minus cos 45 times FAB. And then if we plug that into the calculator, we should have FAC is going to equal, FAB, we already have FAB. FAB is 35.35. So we just times cos 45 times 35.35. And I believe just because it's the reverse of the other one, it should just equal 25. Which is the answer we have in our simulation. So what we've done here is we've already found two of our members. If we go back to our drawing, we can actually write those down and say this over here is going to be 35.35, and this one's going to be newtons, and this one's going to be 25 newtons. And then we can follow that step. We can do it on the other side. We're lucky in this particular scenario that this is symmetric, so we don't have to solve it from both sides. But I will show how we get onto that for our next question. So let's say if we wanted to do this one over here, pink, we'll do this. And this one over here looks like this. Assume that's the right angle. And we know this is at 25. Now we already know what this force is over here. Right? This over here was FAC, and we already have that. We already have what the force of FAC is. It's 25. Now the difference is over here, the force is going to the right. In this scenario, it's not going to be going to the right because we are talking about the force relative to the nodes. Think of it this way: if you have a spring in your hands, if you're pushing a spring in with your two hands, right, you're feeling an outwards force on both of your hands. That's what's happening here. This node is feeling a force going, or it's feeling a force pulling. So like imagine you have a rubber band between your hands. Do I have like a, I don't think I have a hair tie or anything. But let's say you had a rubber band between your hands, you could feel it pulling in both your fingers. That's the same thing that's happening here. If this one's pulling away from the node, this one is also going to be going away from the node. And we know it's 25 newtons. And then we can do the same thing. We can we know this one has to go. This one's going to the left, so this one is going to the bottom right. So down and to the right, and then we can do the same thing. We can solve this using trigonometry again to get our last part. The last thing we have to talk about is our notation. When we have these, I think I have. I'm just going to pause it. Right, so we've already got our forces over here. We have 30 or 35 and 25. And if you look at the example, the solution we have on the left of the screen, we already start to have some positives and negatives, but also, can I zoom in? Nice. We also have colors. So what they're referring to over here, this over here is like our example. Let's ignore that ours isn't 5 newtons. We have a term called tension or compression. And what this is referring to is the force that the member is experiencing. If a member has the force going into the member both sides, so you're pushing the member like you're squashing a Coke can or you're pushing a spring in, that is under compression. Right. Tension is if you're pulling something. So again, if you're pulling like a slinky or a rubber band or something like that, that is under tension. And so what they're noting over there is, we've got the screen, where they write negative, but where it's red is under compression. Yeah, they're saying it's under compression, and blue is under tension. How that relates to our example is, again, think of the example. If I have a hand over here and I want to crush a Coke can in my hand, I want to compress it, my hand is going to feel the force going into my hand. And hopefully yours too. You can feel the force pushing into your hand if somebody wants to crush it. So that's what this force over here, see how this force is going into the node. So this member is being pushed into the node, so this member is under compression. This one over here, the member is being pulled away from the node. So it's like pulling a rubber band, it's under tension. That's I think that's one of the better ways to remember tension or compression, but if you have another way, go for it. So the last thing we do over here is when we're announcing these, let's say we do all the maths, and I can tell you the other one over here is also going to be 35.35 newtons. We just want to say our notation, so we can say C for compression, and we can say T for tension. This over here would be a fully solved version of this truss. All right.